tackling something pretty fundamental, the very foundations of mathematics.
Yeah, it's a big one.
For centuries, right? Math has felt like this solid rock. Fixed axioms, unchanging objects, timeless proofs, all very neat and tidy logic.
Seemingly unshakable.
But what if, and this is the core question today, what if that very foundation, that static view, is actually holding us back? What if it's why we're stuck on some huge problem?
Exactly. Think about things like Gödel's incompleteness theorems. They kind of showed cracks in the system, right?
Right, or the P vis NP problem in computer science, that's a monster.
A huge one. And the disconnect between quantum mechanics and general relativity in physics, that's another persistent puzzle.
Our source material, it suggests these aren't just separate issues. They might all point back to a limitation in how we've traditionally thought about math, this static approach.
Precisely. It might be the common thread.
And this is where it gets really, really interesting. We're diving deep today into a pretty radical new framework. It's called structural calculus, proposed by Mr. Shahryar Ghiasi.
And it's not just a minor adjustment. It's pitched as a whole paradigm shift.
Totally. It reimagines mathematics not as this fixed thing, but as a dynamic emergent science. Almost alive, in a way.
That's a good way to put it.
So our mission today is to explore how this, vibrant new perspective could potentially unlock solutions to those big questions we mentioned. We want to give you a shortcut to understanding this potential future where math proofs are things you can observe and axioms can actually change.
Get ready for some potential aha moments, hopefully. It's quite a different way of thinking.
Definitely. So the core idea of structural calculus, as I understand it, is that maybe the problems we see in modern math come from treating things as fixed. Like mathematical objects are unchanging, truths are absolute, derived from these rigid axioms.
That's the critique, yes. Structural calculus says, let's challenge that. Let's embrace dynamism, interactivity as fundamental.
And it's pulling ideas from all over, isn't it? It's not just pure math.
No, it's a real synthesis. It draws heavily from complex systems theory, how complex patterns emerge from simple rules.
Okay.
It uses category theory, which is all about relationships and transformations between structures.
Right, the connections.
Then there's non-equilibrium thermodynamics, how systems self-organize, how they undergo phase transitions like water freezing. That becomes really important later.
Okay, I see a hint there.
And it also reframes computational complexity theory, looking at computability in a new light.
So it's weaving all these threads together. Very ambitious.
Extremely. And at the heart of it are these things called structural processors. SPS for short.
SPS. Okay, what are they?
Think of them as the fundamental building blocks. But unlike static numbers or sets, they're dynamic computational units. They represent objects or operations, but they're active.
Active, how so?
They're resource-aware. They consume things like time, memory, maybe even energy in a computational sense. They're not just abstract ideas, they're processes.
Okay, like little engines running. You mentioned they have parts.
Yeah, a 5-part definition helps clarify. First, input portals where data comes in.
Got it.
Second, output portals where results go out if the SP is stable.
It's stable. Yeah.
Third, a resource set. This defines what it needs: time, memory, whatever.
Soul for the engine.
Kind of, yeah. Fourth, a stability function. This is its internal algorithm, its logic, how it works.
Engine's design.
And finally, a threshold function. This is crucial. It's basically a switch. Is the SP stable and working, or has it collapsed? Maybe it ran out of memory or hit a fundamental conflict. It only produces output if it's stable.
Okay, that makes sense. Can we have an example? Like, how would you model something simple, say, finding prime numbers as an SP?
Good question. So a prime generator SP, its input portal might take a starting number and maybe a limit, like find primes up to n.
Okay.
Its output portal would deliver the list of primes it finds. The resource set would track, say, memory usage and computation time. The stability function would be the algorithm itself, like the sieve of Eratosthenes, dictating how it uses those resources to find primes.
And the threshold.
The threshold function checks. Does it have enough memory? Has it exceeded its time limit? If yes to either, it might collapse, it becomes unstable, stops processing, no output. It's a dynamic, resource-limited process.
That paints a much clearer picture than just thinking of a static set of primes.
Yeah.
And these SPs, they don't just float around on their own, I assume.
No, definitely not. They connect. The output from one SP can feed into the input of another. They form these complex webs, these structural networks.
Okay, networks of interacting processes, like little computational ecosystems.
Exactly like that. And the dynamics within these networks, how they behave, That's governed by two really important metrics:
Which are?
tension and coherence.
Okay, let's take tension first. It uses the Greek letter tau, tau. What is tension measuring?
Tension, it quantifies conflict. It could be resource contention, two SPs needing the same limited resource at the same time.
Like fighting over memory.
Right. Or it could be functional conflict, deep contradictions. Imagine SPs representing logical statements that contradict each other.
So like requiring a variable to be both true and false.
Exactly. That creates high tension between those SPs. If the tension gets too high, it can make SPs unstable, they might collapse. It's a measure of the stress or friction in the network.
Okay, so high tension is bad. It means things aren't working smoothly together.
Generally, yes, it signals bottlenecks or inconsistencies.
Which brings us to the other metric. Coherence. Is this just the opposite of tension?
It's related, but more holistic. Coherence measures the network's overall efficiency, its functional alignment, its stability. Think of it as how well the whole system is working together.
Harmony, maybe.
Harmony is a good word for it. The source defines it roughly as the ratio of value generated by the outputs to the resources consumed, but importantly, it's heavily penalized by high internal tension.
Ah, so even if it's producing output, if there's lots of internal fighting, the coherence is low.
Precisely. A high coherence network is efficient, stable, it uses resources well, minimizes conflict, and produces consistent, valuable results. Everything is sort of clicking.
This is fascinating. It really does sound like a completely new way to think about computation. But maybe the most radical part of structural calculus is what it says about mathematical proof.
Oh, absolutely. This is where it really diverges.
Traditionally, a proof is, a sequence of logical steps, a deduction.
Right. Step A leads to B leads to C, therefore theorem is true.
But in SC, a proof isn't that. It's described as an observable phenomenon, a phase transition in one of these structural networks. What does that mean?
It means a mathematical statement, say a theorem, is considered proven when the network built to model it reaches a specific state, a state of critical coherence.
Critical coherence.
Yes. It signifies that the network has self-organized into a stable configuration. The SPs have settled, the tension is low enough, the coherence is high enough, and the collective outputs of these stable SPs encode the theorem.
So it's like the network settling into a stable pattern is the proof.
Exactly. Think back to the water freezing analogy. The disorganized water molecules, high tension, low coherence, suddenly snap into an ordered, stable ice crystal structure, low tension, high coherence. That transition is the phenomenon. Here, the network reaching critical coherence is the proof.
Wow. So truth isn't just abstract logic. It's an emergent property of a dynamic system that you can, in principle, observe.
That's the idea, emergent and observable.
Okay, mine's slightly bent.
Right.
But if proofs are dynamic phase transitions, what about the axioms, the absolute starting points of math? Are they still fixed?
That's the next logical question, isn't it? And structural calculus says, no, it introduces dynamic axiomatics.
Dynamic axiom, so the bedrock can shift.
It can evolve. The idea is if the internal tension within a network representing an axiomatic system stays above a certain critical decay threshold for too long.
Meaning there's a persistent, deep conflict or inefficiency in the rules themselves.
Exactly. Then those underlying axioms can actually undergo transformation. Or even decay. New, more stable, more coherent axioms can emerge to reduce that tension.
So the rules of the game can change themselves to resolve internal contradictions. That's wild. Can you give an example from math history where this might apply?
Russell's paradox is the classic one. The old, naive idea of sets. Basically, any collection you can describe forms a set led to a paradox.
The set of all sets that don't contain themselves.
Right. Trying to define that creates, in SC terms, infinite internal tension. It breaks the system. That high tension, according to this framework, forced the naive axiom to decay.
And transform into
The more restricted axioms we use now, like in Zermelo-Fraenkel set theory, ZFC. These axioms avoid the paradox. They operate with much lower internal tension. SE interprets this not just as mathematicians fixing a problem, but as an internal self-correction process of the mathematical structure itself.
Okay, that's a profound reinterpretation. So let's connect this back to those big unsolved problems. How does structural calculus offer a new angle on, say, P versus NP?
Right, the PVS-NP question. Can every problem whose solution is easy to check also be easy to solve?
That's the gist.
In SC, you model hard NP complete problems like 3SAT Boolean satisfiability using these structural networks. Each clause in the 3SAT problem becomes an SP.
Okay.
Tension arises when different clauses demand conflicting truth assignments for the variables. You need X to be true here, but false over there.
The conflicts we talked about.
Exactly. The network's overall coherence goes up as more clauses are satisfied and tension goes down. Finding a solution means finding a state of variable assignments that satisfies everything, maximizing coherence.
So where does the P vs NP part come in?
The hypothesis is this. An instance of a problem like 3SAT is solvable in polynomial time. The P part meaning efficiently, if and only if its corresponding structural network reaches that critical coherent state within a polynomially bounded amount of time or resources.
Has anyone actually, run simulations to see if this happens?
The source material does report empirical data from simulations. They looked at 3SAT, graph coloring, traveling salesman, all famous NP-complete problems.
Oh.
And they found that the convergence to a solution state, marked by hitting that critical coherence threshold, seemed to consistently happen within polynomial time bounds. For 3SAT, they reported something like O and 3.2 minus 0.1.
Whoa, so the simulations suggest.
They suggest that the apparent hardness of these problems in traditional computer science might be an artifact of our static models. Introduce dynamics, self-organization, coherence, and maybe, just maybe, P does equal NP. SC proposes a mechanism for how that could be possible.
That would be absolutely revolutionary. Okay, what about Gödel's incompleteness theorems? The idea that some true statements just can't be proven within their own system.
SC gives this a dynamic twist, too. An undecidable statement, from this perspective, is one that generates infinite or insurmountable tension within the SP network representing that formal system. You just can't resolve the conflicts it creates using the existing rules.
Okay, so it breaks the system, like Russell's paradox did.
But instead of seeing it as a dead end, SC sees it as a trigger. That unbearable tension activates axiom decay.
The dynamic axiomatics we discussed.
Right. The system transforms itself, evolves its axioms into a new system. And in that new, evolved system, the statement that was undecidable might now become decidable.
So incompleteness isn't a wall, it's a catalyst for growth.
Yeah.
A signal that the math needs to evolve.
That's the reinterpretation. It's a dynamic process, not a static limitation.
Okay, one more big one. Quantum gravity. The quest to unite quantum mechanics and general relativity. Seems like a huge leap for a mathematical framework.
It is ambitious, but the proposal is fascinating. Structural calculus suggests modeling spacetime itself as a structural network. Let's call it NST.
Spacetime. As a network of SPS, what are the SPs in this case?
Think of them as fundamental granular units of spacetime, maybe something like Planck volumes, but dynamic.
Wow.
Active little bits of spacetime fabric.
Okay. And tension and coherence.
Right.
What do they represent here?
This is where it gets really interesting. The tension between these spacetime SPs is proposed to be directly related to local spacetime curvature and energy momentum density.
So like near a black hole where gravity is intense and spacetime is warped.
The tension in that part of the spacetime network would be extremely high, lots of stress.
And coherence.
Coherence in the NST network is proposed to be related to things like local entanglement entropy, gravitational entanglement. It's a measure of how ordered and interconnected the space-time structure is at a fundamental level.
Wow. So how does this connect to, say, Einstein's equations, which describe gravity so well on large scales?
The idea is that Einstein's field equations, the description of classical smooth spacetime, emerge as the effective description of this network when it's in a state of very low tension and very high global coherence.
So classical gravity is the macroscopic view of this underlying network being very calm and stable.
That's the proposal. And quantum phenomena, like quantum fluctuations, those could be seen as tiny local deviations from that perfect coherence, little regions where tension is higher, preventing the network from settling into that smooth classical state.
So it provides a potential bridge. By seeing both classical and quantum effects as different regimes of behavior in this underlying space-time network.
It offers a conceptual framework, yes. Quantum gravity would then be the study of the low-coherence, high-tension regimes of this space-time network, where things are far from smooth and classical.
This is really pushing the boundaries, and it sounds like this dynamic nature makes it suitable for simulations. You mentioned structural programming.
Exactly. Because it's about dynamic processes reaching stable states, it naturally suggests a different way to program. Instead of just writing instructions to get a fixed answer, a structural program would aim to guide a network of SPs towards a state of high coherence.
So the program would be trying to minimize tension, maximize coherence, and let the solution kind of emerge.
That's the concept. Imagine iteratively adjusting things within the network until it settles into a stable, coherent configuration that represents the solution.
And does this connect to anything happening in, like, actual computing hardware?
Well, what's particularly intriguing are the parallels people are drawing between structural calculus and things like quantum annealing and quantum computation.
Ah, the quantum computers that are being developed now.
Precisely. You could potentially map the SPs onto qubits.
Right.
Tension could correspond to concepts in quantum systems like quantum frustration or the strength of certain fields that try to pull qubits in different directions.
And coherent.
Coherence might map onto measures of quantum entanglement or the probability of the quantum system settling into its lowest energy state, its ground state.
So finding a solution in SC, high coherence,
Mhm.
might be physically analogous to a quantum computer finding its ground state.
That's the exciting possibility. And there's some early experimental evidence, for instance, from D-Wave's quantum annealers, that shows solving certain hard problems correlates with the system settling into these low-energy states. It hints that these computational phase transitions that SC talks about might actually be physically realizable phenomena.
Which leads to this idea of empirical mathematics,
Yeah.
where you could almost see a proof happening in a simulation.
That's the vision. Theorems as observable phenomena. It's a radical departure.
So wrapping this up, structural calculus really represents a potential sea change, doesn't it?
It's presented as a profound paradigm shift, yes, moving math away from this static, almost platonic ideal,
Towards something dynamic, emergent, maybe even empirical.
where proofs are phase transitions, not just deductions, where truth itself becomes context-dependent, dependent on the resources, the network structure.
It introduces a subtle but really deep contextuality into math.
And beyond the big theoretical claims, resolving paradoxes, maybe unifying discrete and continuous math, potentially showing PMP.
Which are huge in themselves.
It also gives us a rigorous language, potentially, for describing any self-organizing computational system. Think about AI.
How so?
Well, you could perhaps reinterpret AI training as a process of guiding a network, the AI model, to minimize its internal tensions and maximize its coherence, its ability to produce stable, useful outputs based on its inputs.
Guiding it towards an optimal configuration.
Exactly. Now, of course, there are challenges, big ones. How do you precisely calibrate critical coherence? How do you quantify abstract resources for really complex SPs?
It's not all figured out yet.
Not by a long shot, but it offers this compelling alternative vision, a potential mathematics for the 21st century, one that feels much more connected to physics, computation, and complexity. It makes math feel alive.
It really does. So as we bring this deep dive to a close, here's something to think about. If mathematics isn't this rigid, unchanging thing, but more like a living system, a kind of physics of computational matter, as you put it,
Where theorems are observable, axioms adapt.
what does that really imply about discovery versus invention in math? Are we discovering timeless truths, or are we inventing systems whose emergent properties we then observe?
Does it maybe suggest that the universe itself is fundamentally computational and what we call physics and math are just us observing the behavior of that computation?
It's a seriously provocative thought to mull over. Definitely encourages you and us to keep exploring this fascinating, potentially revolutionary frontier of dynamic mathematics.